to the second session of the day. We're very delighted to have Ramon van Handel from Princeton University, who's going to talk to us about Fourier and harmonic analysis on the discrete cube. So Ramon has asked that you should feel free to ask questions. So to try to make it easier, if you want to ask a question by voice, just raise your hand and I'll try to pass it on.
All right. Thanks very much, Nike, for the introduction and for the invitation. First of all, I'm going to do exactly the opposite of talk about Fourier analysis on the discrete cube, but I'm about to explain that. The other thing is that, you know, before this lecture, I decided to look up the meaning of the word boot camp. So according to the dictionary, at least the one I consulted, the boot camp, a noun, is a military training camp for new recruits with strict discipline. So I think, you know, I guess I'm in charge of the training part, and then maybe Nike will implement the strict discipline. As Nike said, you know, everybody should feel free to just ask questions. And as far as I understand, what she means by raise hand is click on the button that says raise hand, not actually raise your hand, because probably nobody will see that. So if you raise your hand, then the Nike can enable your microphone and you can ask a question directly, or you can use the Q&A, whatever you prefer, but I probably won't see it. All right, so let's talk about the discrete cube. What is the discrete cube? It's not a very sophisticated object. Here it is, -1, 1 to the n. That's the discrete cube. So this is just a set of strings of n bits. I will denote my values of my bits by -1 and 1 rather than 0 and 1, but okay, this is not a big deal. So we're looking at strings of n bits, and what we're going to look at are functions on the discrete cube, right? So for example, we will look at a function. If we look at a function from -1, 1 to the n that can only take 2 values, such a thing is called a Boolean function. And they show up all over the place, you know, in computer science. You know, this is an algorithm. You stick in n bits and it spits out 1 bit, right? Or you can think about it as an outcome of an election. I have n voters. Each one of them votes Republican or Democrat. And the outcome of the election is either Republican or Democrat, and there's a function f that determines, you know, how the votes of the individual voters are put together to determine the outcome of the election. Right? So this is a very classical application, very current right now. But of course, there's no reason to just spit out 2 values. You can take a function that spits out any real number, right? So you just have an algorithm. You put in n bits, and for every sequence of n bits you put in, it spits out a number. So I guess this is just called a function. Something that we will spend quite a bit of time talking about is a function that doesn't take values in the reals, but that takes values in vectors, right? So for every sequence of n bits, it spits out a vector in some norm space. So this is a vector valued function. And we will have a lot more to say about these type of functions. So, you know, it's a very general object, and we will think of them as being random, of the input bits as being IID random bits. So I'm going to think of them as being plus or minus 1 with probability 1/2. You can, of course, consider other probabilities as well, but this is the standard thing, right? So if you think about it that way, then these are all random variables, right? Because I stick in a sequence of random bits, and outcome's a random outcome of this function. So this is not much to look at, right? I mean, it seems like I've either described nothing or everything. In either case, it doesn't seem, what can you do with these things? But of course, these things show up in all sorts of applications, in discrete probability, in theoretical computer science, in many areas of pure mathematics, in social choice theory, and other places. And they have actually rather a surprisingly rich theory. I mean, the theory of these type of functions is really quite amazing, considering that the definitions basically impose nothing, more or less. So I should start by saying that I'm hardly an expert on this theory. So there are very good books written about it. So here are some very nice texts. There's one by O'Donnell called The Analysis of Boolean Functions. There's a book by Gabon Steiff. And I really have nothing to add to these books. Okay, so I'm going to try to take a little bit of a different tack and make some remarks that fall a little bit outside the usual approaches. So let me talk a little bit about the types of methods that have been used to study these type of functions. So I would say that the analysis of functions on the discrete cube is sort of overwhelmingly influenced by methods of Fourier analysis, and sometimes the analysis of Boolean functions is even viewed as sort of synonymous with analysis, Fourier analysis on the Boolean cube, right? So the Boolean cube -1, 1 to the n is a group. It's a very, very simple group. And so there is a Fourier transform on this group. It's a commutative group. There's a Fourier transform on it. And so you can Fourier transform functions. And you can study a lot of these functions by expanding them in their characters, etc. And this has turned out to be hugely influential. So there's many, many names associated to this. So one of the first ones to really study this systematically is Aline Bonamy, but then there was Kahn Kalai Lineal, etc. We're gonna, okay, many, many, many more. This is what Irit would call the O1 sample of the, the huge number of people who have developed this theory. It has really been very, very influential, and so much so that often when one starts thinking about these type of problems, one starts down by writing immediately the Fourier expansion, and then one starts working with these type of things. Okay? And there are many beautiful methods of harmonic analysis that can be used to study these type of functions. I deliberately do not want to talk about this. So these lectures are absolutely not about Fourier analysis, and I'm not going to do any Fourier analysis whatsoever. Okay? So what I want to talk about is other types of methods. So there are a lot of open problems in this theory, and recently a few of these open problems were solved. And in the problems that I have in mind, it turned out that Fourier analysis is exactly the wrong way to think about these problems. You really should just go back to the drawing board and use find different ways to think about these problems. And these types of methods, I think, are much less well appreciated. Okay? So let me list a few that I particularly like, roughly in decreasing order of sophistication. So there's a very amazing method using non-commutative probability, which is due to Françoise Luce-Picard. This is really, I will have more to say about this method later. This is a really fascinating idea that you can use quantum methods to study classical questions about functions on the Boolean cube. And there are certain inequalities that we still don't know how to prove in any other way. So this is very surprising, I think. So this has been developed by François Luce-Picard in a number of papers. Then recently, there has been a series of papers by Ramon and Eldan, which use stochastic calculus, which is another type of method that is not classical in this type of area. And last, very recently, with Pata Ivanisvili and Sasha Volberg, we managed to solve some old open problems in the analysis of Boolean functions in Banach spaces using basically nothing, okay? No machinery whatsoever. So let me call this embarrassingly elementary probability. So with Pata Ivanisvili and Sasha Volberg. It's sort of surprising that's, methods that are so elementary are able to solve problems that had been open using sort of sophisticated machinery. So what I would like to do in these 4 lectures is I want to mostly talk about the 4th thing because it's very elementary and I can very easily introduce the basic notions. And then my hope is that I will actually be able to prove for you everything. Okay, so if my aim is to give you full proofs of everything I do from scratch. I don't know if we will actually manage, but we will see. So let me tell you what I plan to cover. So I plan to talk about 2 very different recent developments. First one is the theory of vector valued inequalities on the cube, which is the theory that we developed with Bata and Sasha. And the completely different topic is a recent result of Ronen Eldan and Renan Gross, which is a solution of a conjecture of Talleyrand and Boolean functions, which is due to Ronen. Which they solved using methods of stochastic calculus, but actually I will give you also a very elementary proof of this using the same techniques. Okay, so that is my plan for these 4 lectures, and to show you how one can prove such inequalities that seem to be outside the reach, or at least as far as we know, of more sophisticated methods. Okay, so this is my plan, and we will see how far we get. So very good. So for this lecture, I want to jump straight into it, and I want to start by solving a toy problem. Toy problem. This is a problem that certainly doesn't need any new ideas, which is the Poisson inequality on the discrete cube. This inequality is probably the most basic inequality in existence. Using Fourier analysis, this is a 1-line triviality. Okay, so I'm going to give you a much less nice proof of this using basic probability, but it is an excuse for us to develop the techniques that basically we will use in the remaining lectures. Okay, so I want to introduce a number of basic ideas that we will be able to use later to prove more sophisticated things. So let me try to explain what this inequality is. So let's take a function on the discrete cube. And for now, we work with real valued functions. And I now need to explain to you what is the notion of a derivative on the discrete cube, right? Everybody knows what the calculus derivative is, but what is the derivative of the discrete cube? So I'll work with the following notion. So if I take the derivative with respect to the ith coordinate of the function f of epsilon, by definition, what will I do? I take the function of epsilon. So this is epsilon 1. This is just a function of the input string epsilon, minus the function where I flipped the ith bit, and we'll divide by 2. Divide by 2 is just a normalization, because epsilon, if we take 1 minus 1, you get 2. So you would like the derivative of epsilon I to be 1, right? This is the notion of derivative we'll use, which is just a sort of analog of the classical notion of a derivative on Rn. But unlike the classical notion of derivative, it has some basic properties. So let's do some basic exercises before I start actually using this derivative, just so we have an idea how it works. So for example, if I take the second derivative, di squared f, so I take the difference between the function and when I flipped the ith bit. If I do it again, I just get back the derivative again, because you just plug it into this definition, right? I mean, you should check it, right? If I do it twice, I get back the same thing. So unlike in classical calculus, where the second derivative, of course, is very different than the first derivative, on the discrete cube, if you work with this notion of derivative, in a moment I'll show you another notion of derivative, but if you work with this notion of derivative, the second derivative with respect to the coordinate is just the same as the first derivative. So you should keep this in mind. The second thing, which is easy to see from the definition, if I take derivative with respect to in two different directions, then I can always exchange them. This is the same as usual. Now, there are different conventions for what you define to be derivatives in Boolean analysis. So there's another notion of derivative that I'll denote partial if, which is maybe a little bit closer to what you think of as a calculus derivative. What I do is I take the function where I set the ith bit to 1, and I subtract the function where I set the ith bit to -1, and I divide by 2. So in di of f, I've just taken the ith bit, the function of epsilon, and then I subtracted the function where I flipped the ith bit, right? In this partial I of f, I've taken the function where I've set the ith bit to 1 minus the function where I've set the ith bit to -1. Right? These two things are the same up to a sign. Then di f of epsilon is just equal to epsilon I partial I f of epsilon, right? Because if epsilon I is 1, right, then di of f of epsilon just has a 1 in the first term and a -1 in the second term. But if epsilon I is -1, then di f of epsilon has a -1 in the first term and a 1 in the second term, so it just flipped, right? So then you multiply it by the sign. Right? So you can trivially go back and forth between these two notions of derivative. I prefer the di derivative. The delta I derivative, the partial I derivative, has the advantage that partial I of f doesn't depend on epsilon I, right? So what you can see here, for example, is that di f of epsilon is anti-symmetric in epsilon I, right? Because partial I f of epsilon doesn't depend on epsilon I, and I multiply it by epsilon I. So if I flip the ith bit of di f of epsilon, I just get minus di f of epsilon. Okay? So this is a little bit boring right now because we're actually not doing anything, right? But I will use these type of computations in a bit, so it's good to have them out of the way. Okay. Very good. So let me now formulate the Poincare inequality. So here is the Poincare inequality. Carré inequality. So the Poincare inequality says that for any function f on the discrete cube, the variance of f, remember we think of f as being random, right? Because I plug in n IID bits, right? And I want to look now at this as the output of this function as a random variable. So what is the variance of this function? How large are the fluctuations? The Poincare inequality says that the variance of f is bounded by the expectation of the Euclidean norm of its derivative vector squared. So if I want to just pedantically spell out what I wrote here that the expectation of f squared minus the expectation of f squared is less or equal to the sum I is 1 to n of the expectation of the derivative in the ith directions. So it's exactly what you think of. So this inequality is probably the most basic result in the study of Boolean functions. It is one of the simplest examples of a concentration inequality, right? So one of the key points of this inequality is that the constant here doesn't depend on dimension. Actually, the constant is 1, okay? But more importantly, the constant here doesn't depend on the dimension n, on the number of bits I stick in. So what this inequality is saying is that, for example, the way you could view it is that any Lipschitz function has variance of order 1. Independent of the dimension, right? Even if I take a very, 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 very high dimensional function, right? If the function is sufficiently smooth, if it's Lipschitz, then its probabilistic fluctuation, its variance has to be of order 1. Right? So this is exactly a high dimensional phenomenon of the type that is in the title of this series. And this inequality plays a very important role in proving many different things.
Ramon.
Yes.
Ramon, you have a couple of questions.
Great.
One is,
what are they?
is it related to the F1 inequality?
Yes.
Good. and the second one,
it can be deduced from it trivially.
And the second one is it necessary to assume the uniform distribution on X to make this statement?
So the uniform distribution on X, no. I mean, one can consider other distribution of now you get a constant, which might depend, for example, on the probability P, right, of the bits. Or if you don't take them to be independent, it will have to depend on the correlations, et cetera, et cetera. So all of these things that I'm going to discuss, you know, of course, you could view them in a much bigger framework, and then you can prove much more general results. But I'm going to concentrate throughout all 4 lectures on the situation where all of the strings are equally likely. This is the basic case that one should understand, and after that, one can hope to study more sophisticated things. Okay? But yes, of course, these type of inequalities are very, very useful in many different settings, and particularly the Poincare inequality, which is very simple, can be you know, studied in a very, very, very general frame, right? So this is just one very special case. All right, so good. So this is a very basic inequality. Let me give, just for fun, another interpretation. Suppose that f is a Boolean function, right? So suppose that f is the outcome of an election, right? I have n voters. They have Democrat or Republican, and the outcome is either Democrat or Republican, right? So f is always takes the values -1 or +1. So then what is di of f, right? What happens, what it measures is what happens when ith voter flips their vote, right? Suppose the ith voter flips their vote. If that affects the outcome of the election, then di of f will be equal to 1 or -1. But if that doesn't, if the ith voter flipping their vote doesn't affect the outcome of the election, then di of f will be equal to 0. So in this funny example, this quantity over here is nothing else than the probability that if the ith voter flips their vote, that they will change the outcome of the election. That's something called the influence. If you have, for example, a voting scheme that that the probability of one of the two parties is the same as the probability of the incoming bits, right? It's a fair election, then the variance will be of order 1. It will be 1/4. And then this is saying that the sum of the probability that of each voter influencing the election is at least 1/4, right? Which means that there is at least one, no matter what the voting scheme is, there's at least one voter that has at least probability 1 over the number of voters of influencing the outcome of the election. This is one of the basic results of social choice theory. Actually, it turns out that this result can be much improved, and I'm not going to talk about it, but I'm just giving you different interpretations of this type of theory. So I realize that in a lot of these lectures, I'm not going to give a lot of motivation or applications, because you can find all of this in all of these beautiful books that I put on the first slide. So I really want to emphasize more the techniques that I'm going to be using, but it's still good to discuss a little bit. So very good. So let's try to prove this inequality. Where do we start? So the very first idea I want to introduce is a very basic idea that we'll see in a number of different situations. So the first idea is something called the interpolation method. And let me phrase it very generally. So I'm going to write next to it the names of Bakri and Emery, but actually the same method is used in different contexts by different people. So could write ... So what's the idea? We want to upper bound the variance, right? What is the variance of a function? It is the expectation of f squared minus the expectation of f squared. So the key point here is we want to bound the difference between two quantities, the expectation of f squared and the expectation of f squared. Right? Each of these quantities themselves might be very large, right? But it can then still be true that the difference between them is very small. Right? So bounding differences of two things is always harder than bounding just the magnitude of one of these two terms. So how would you bound the difference between such two terms? Well, what you could do is you could try to design a function that interpolates between these two guys, right? So try to find a function phi of some parameter t from 0 to infinity, such that phi of 0 is the expectation of f squared. And let's say phi of infinity, if I let t go to infinity, will be the expectation of f squared. So this function, just as I increase t, it interpolates between both sides of this inequality of this quantity that I want to compute the difference of, right? So I design some interpolation between the left and the right term, right? So if I had such a function, then how could I express the variance of f, right? Well, that would be phi of 0 minus phi of infinity. And then I could just apply the fundamental theorem of calculus, right? Because this is minus the integral from 0 to infinity of d dt of phi of t dt, right? That's nothing else than the fundamental theorem of calculus. If I integrate the derivative, I get phi at one endpoint minus phi of the other endpoint. So the basic idea of interpolation is, okay, you want to bound the difference between two things, find some function that interpolates between them, then apply the fundamental theorem of calculus, and then what you hope is that this derivative of that function is related to the quantity you want on the right-hand side of your inequality. So in our case, right, on the right-hand side of the inequality, we want something involving the derivative of the function f. Here we have not the derivative of f, but we have the ddt of the interpolation. But it's very natural to hope that if you have a good interpolation, then the rate of change of the interpolation will be related to the rate of change of the function itself. And then you can see why the interpolation method should allow you to bound something like the variance of f by a derivative, right? This is a very vague idea, and we will see several different incarnations of it, okay? But this is a basic idea. So it's a very general mechanism. And of course, the devil is in the details of how do you actually construct this interpolation. It is a classical idea of Bakri-Emery, but again, I think, variants of this type of idea have existed for a long time, that it's very natural to construct such interpolations by a probabilistic construction. Okay, so let me give you a probabilistic construction. So basically what we're going to do is we're going to construct this interpolation from a random walk. The random walk will be in continuous time. Okay, so because phi of t, in order to take the derivative, has to be in continuous time, and I'll define it more precisely in a moment. Okay? But for now, let's just be vague. So let's take xt to be a continuous time random walk on the discrete cube. Right? So at time 0, we start at some initial point on the discrete cube. And then as time moves on, every once in a while, we jump to some neighboring point on the discrete cube. And then we jump to some name randomly. And then we randomly jump to some neighboring point on the discrete cube. Every time we just flip some bit randomly. And then we flip another bit randomly. And we keep doing this over and over again. Right? So we just take a random walk where we keep flipping random bits. Right? Now, I will just define in a moment how you do that in continuous time. Let's introduce this object. For any function f, let's denote by ptf, that's another function. This is the expectation of this function of the location of the random walk at time t, given that I started at time 0 at the point epsilon in the discrete cube. Okay, so this is a definition, right? So every function f, we can compute the expectation of that function of its location at time t, given that we started initially at the point epsilon, right? And that defines a new function of the initial condition. So this object, if you're used to it, it's called a Markov semigroup. But actually, I'm just going to do all sorts of manual computation. Right? So let me come to the point. What properties does this function satisfy? Right? Well, first of all, if t is 0, right, the expectation of the function of the position at time 0, given that at time 0 I'm at the point epsilon, is just that function at the point epsilon. Right? That's obvious. Right? So at time 0, p0 of f is just f. On the other hand, what happens if I let time go to infinity? Well, so I start at the point epsilon, and now I start doing a random walk around the cube. Now, as you know intuitively, right, if I start doing a random walk in a finite set, right? It's like the discrete cube. After a long time, right, the probability of ending up at any particular point gets more and more and more uniform, right? So after a long time, you go to steady state, right, where the probability of being at every point becomes equal, right? So the random walk will, the distribution of the random walk will converge to steady state, right? So if I let time go to infinity, what we expect is that this function, the expectation of f xt as t goes to infinity, should no longer depend on where I started, right? The random walk goes to steady state. And as time goes to infinity, this just goes to the expectation of the function. So these are the two extremes. Initially, I'm at the point epsilon. After a long time, I go to steady state, where I'm just uniformly distributed on the discrete cube. I'm going to give an explicit construction where we will see that this is true, okay? But I'm just giving some intuition. So this function PTF interpolates between f and its expectation. So if you had such a probabilistic construction, then what could we take our function phi t to be? Our function phi t, we can take it to be the expectation of PTF squared. So if we do that, then phi 0 is just the expectation of f squared. And as time goes to infinity, this will become the expectation of f squared, or the expectation of f is not random. So this becomes the expectation of f squared, right? And this is exactly the interpolation that we want, right? So the difference between phi 0 and phi infinity, which is the variance of f, is exactly equal to minus the integral from 0 to infinity of d dt of the expectation of PTF squared dt, right? Which is an identity. So I've done nothing else than take the interpolation idea that I had on the previous slide, but I've created the interpolation. It's very natural to do this using a probabilistic model of random walk, right? Because a random walk will interpolate naturally between the steady state, which is the expectation of the function f, and the initial condition, which is the function f itself, right? And that exactly allows us to go between, for example, the expectation of f squared and the expectation of f squared. And so if we have such a construction, right, then in some sense, all we have to do is bound the rate of change of the random walk as a function of time and see what it is. And what I claim is that if I do this correctly, I'm indeed going to get the Poisson inequality. Okay, so we're going to see that next. So these are two sort of vague basic ideas, but these are, morally speaking, these are really the only two ideas I'm going to use in the 4 lectures, except for one more idea that we will see in the next lecture. Okay. Good. So now at this point, I have to actually start doing some computations. So I have to tell you how I actually construct this random walk in continuous time. And then the rest of the story, right? So once I have constructed the random walk, I have to compute the derivative of the expectation. That will become a matter of calculation. It's just elementary probability theory. Okay? So let's do this exercise and see what happens. So let me start by constructing this random walk on the discrete cube. And again, we have to do our homework a little bit, but this will pay off because I'm going to use the same construction. It's the only construction I'm going to use in all 4 lectures. Okay, so this is an excuse for us to just introduce this construction in the relevant notation. So how do we define the random walk? Let me just, let me just say it colloquially in some sense. So this discrete cube has n coordinates, right? It's -1, 1 to the n, so there are n bits. Right? So what we're going to do is we're going to wait for a random time, and then we're going to flip one of the bits. We're going to wait for a random time, and we're going to flip one of the bits. Right? So what I have to do is I have to introduce some sort of clock, which tells me when I flip one of the bits, and then I will flip the bits when the clock ticks. Right? So here's how we do it. So to each coordinate, we attach an independent Poisson process with rate 1. And if you don't know what this is, I'm going to give you an even more pedestrian thing in a moment. I'll just draw a picture. So don't worry about it. But for now, let's attach to each coordinate an independent Poisson process of rate 1. A Poisson process is just something that ticks every once in a while at a random time. And each time that the coordinate I ticks, we sample it from the uniform distribution. So this is the construction, right? So to every coordinate, we attach a random clock. When the clock of coordinate I ticks, I just flip a coin, right? And I just set the bit I to the outcome of that coin. Then the next time the clock ticks for that coordinate, I again flip a coin and I set the bit I to the outcome of that coin. If the coordinate of another, if the clock of another coordinate ticks, then I flip a coin and I set that guy to the outcome of the coin, right? So if I draw a picture, so here I'm just drawing a picture of a Poisson process. So you don't really need to know what it is. So for example, here is the clock for coordinate I, here's the clock for coordinate j. These axes denote time, right? So how does it work? So for example, for coordinate I, every once in a while, the clock is going to tick. So at that time, across means that it ticks at that time. And then maybe later the clock ticks again for that coordinate. Maybe it ticks there. These are random times. And the coordinate j independently has its own random clock. So it might tick here and it might click here, etc. Right? So these crosses just denote the random times at which these clocks for the different coordinates click. And the definition of a Poisson process is that the times between clicks of the clock are exponentially distributed with parameter 1 and independent. Right? So you just wait an exponential amount of time, you click, then you draw another exponential random variable. That's how long you have to wait until the next click, etc. Right? And you do this independently for every coordinate and for every time that it clicks. And every time that, for example, so at this time where the coordinate j first click, you flip a coin and you just set the value of that bit to the outcome of the coin. Then the next time that the coordinate j clicks, you flip a coin, you set the coordinate j to the output of that coin. And when the clock of coordinate I clicks, then you flip a coin and you set the outcome of that bit to the outcome of the coin, etc. So I hope this is clear. What I said, this is just a very explicit way of constructing a random walk on the discrete cube in continuous.
So is it okay if I interrupt for a question?
Absolutely.
So we had a question that is an explicit construction necessary, as in, are there some constructions for which the proof, some constructions of the random walk for which the proof wouldn't yield the right inequality?
I am never going to use this actual construction. This is a very good question. In fact, I'm going to strip this construction of all of its interesting structure. So for example, if you look in the papers of Ronen Eldan, for example, then where he uses stochastic calculus, then he does use the actual construction because he uses the fact that you know exactly what the paths of this process look like when they flip. And I'm not going to do this at all. I'm only introducing this as motivation because I think it's useful to have a picture in your head about what's going on, probabilistically. But in fact, we're not going to do anything, and I could define everything just by writing down a bunch of formulas from the very beginning. But it's more intuitive to have a picture in your head of what's going on. Even if you don't use it, the picture that you have in your head can help you prove theorems because it gives you intuition for what's going on. But it's a very good question. Were there more questions right now?
I think that's it for now, yeah.
Okay. So now let's get to the point. So I'm immediately going to strip this of all of its structure. Okay. So let's compute the distribution at time t of the random walk. So what is the probability that the ith coordinate at time t takes the value epsilon? So epsilon is either 0 or 1. Okay, so what's the probability at time t the ith coordinate is equal to epsilon 0 or 1, given that at time 0 we started with the ith coordinate being the same thing, right? So what is the probability at time t the ith coordinate has the same outcome, has the same value as initial? Right? There are only two possibilities, right? So the probability that's minus epsilon will be 1 minus this probability. Well, it's basically obvious, okay? So let's look. So for example, let's pick this coordinate I, right? So what's the probability that at time t, if we fix some time t, right? What's the probability that the clock hasn't yet ticked, right? That's the probability that this first exponential random variable hasn't yet happened, right? So that's e to the minus t. That's just the exponential distribution. So with probability e to the minus t, right, the clock has never ticked on the ith coordinate, and therefore the value currently must be the same as its initial condition. But there's another possibility, which is that if the first clock has ticked at some point, right, well, after the first clock ticks, you always just replace it with something that is probability 1/2 1 and probability 1/2 minus 1. And even if it clicks again and again and again, you always replace it by something that's probability 1/2 1 and 1/2 minus 1. So if the first clock hasn't ticked yet, then you're the same with probability 1. But if the first clock has clicked, then you always are, whatever value you have it with probability 1/2. So this is the probability, right? It's just basic undergraduate level probability. So the probability that at time t, you have the same value as where you started is this number, right? Which is nothing else than 1 plus e to the minus t over 2. So this tells you what happens with one bit. And of course, each of the bits by construction is independent, right? So the distribution of the whole vector of xt for all of the coordinates is just independent copies of this random variable. So let me summarize what we've computed. Fact. I've just proved it, basically. But I will introduce some notation. So this notation I'm going to be using in the rest of the lectures. So let's introduce some random variables psi I of t, which are I is 1 to n, are independent, okay, random variables. With what distribution? So these are signs. The probability that psi it is +1 or -1 is 1 plus or minus e to the minus t over 2. So psi I is +1 with probability 1 plus e to the minus 2 over 1 plus e to the minus t over 2, and it's -1 probability 1 minus e to the minus t over 2. Okay. So this psi it is just going to be the random variable. If it's +1, this psi it says that currently you have the same value as the initial condition. And if psi it is -1, then that says that currently you have a different value than the initial condition. Right? That's going to be the role of these psi its. And in terms of these psi its, we can just express this pt f of epsilon, right? So this is the expectation of f of x0 given, this expectation of f of xt given x0 equals epsilon. I can just express it as follows. I take the expectation with respect to these x's of f of epsilon 1 xc1t until epsilon n xn, which I will just denote by expectation xc of f of epsilon xt. So just to emphasize what is going on here, so when I write expectation with a subscript xc, I just mean I'm only taking the expectation with respect to the xc coordinates, and the epsilons are fixed, right? Because this is a function of epsilon. So epsilon are just some fixed signs, right? So what did I do here? If, for example, epsilon 1 is 1, right? That means at the time 0, the first probability 1 plus e to the minus t over 2, right? Which is exactly the psi 1t, right, being 1, right? So psi 1t times epsilon 1 is epsilon 1 if psi 1t is 1, and it's minus epsilon 1 if psi 1t is minus 1, right? So this computation that I did over here is just contained in this very simple notation. So I'm just using these random variables psi it to keep time what is the distribution of the random walk. And this is the only thing we're going to use in the entire rest of the lectures. Okay, so so if you want this random walk, it's just motivation. Now the nice thing is that now that we have an explicit formula, right? So here we have an explicit formula for this object that interpolates between PTF and F. Everything else just becomes a matter of computation. Okay, so let me write down a lemma. The lemma is going to be a short laundry list of things we can compute, and I will compute them in a moment. But let's just say that these things are just, I start with this explicit formula and I take some DDTs or I compute some things, okay? And so let me show that we can now complete the proof of the Poincare inequality once we just do these explicit computations. These are very elementary probabilistic computations. So let's first do that. So I don't love these type of lemmas because, I'm just going to say, oh, I can compute this, I can compute this, I can compute this, and I will compute it in a moment. It feels like a little bit of a laundry list, but actually, these computations, we're just going to use them over and over again in the remaining lecture. So we might as well get them out of the way now. Okay, so let's call this random walk calculus. So what properties do we have? First of all, the expectation of PTF is just going to be the expectation of F. This is called stationarity. Then remember that in order to do this proof by interpolation, we have to compute DDT of PTF, right? So DDT of PTF turns out to be equal to some operator acting on PTF. This is called the heat equation, where this object, which is called the Laplacian of F, is minus some I is 1 to n of the ith derivative of F. This is called the Laplacian on the discrete cube. Now, you may be a little bit confused because you probably think of the Laplacian as being the sum of the second derivatives of the function F, right? When you learned in calculus, right, what the Laplacian was some I df dxi df squared d squared f dxi squared, right? But remember that di squared f is equal to dif, right? So on the discrete cube, these things are the same. Now, because of this, we can solve. Here we have a differential equation for PT, which we can solve. So this says that PT is e to the t times Laplacian. I'll explain in a moment what this is, which means in particular, for example, that Laplacian PT is PT times the Laplacian, di PT f is PT dif, etc. Okay, so we have now some sort of calculus. We can move the derivatives inside and outside the PT. These type of tricks will be very useful for us. Third, what happens if we take the expectation? So the expectation of F times the Laplacian of G will be nothing else than minus some I is 1 to n of the expectation of dif times dig. This is nothing else than integration by parts. If you think of the Laplacian as being the sum of the second derivatives, if I take expectation of f times the second derivative of g and I integrate by parts, I get the expectation of derivative of f times the derivative of g. Okay, so that's integration by parts. This is called the semi-group property. And the fourth inequality is a very interesting one. It says, what happens if I take PTF, I take the derivative with respect to the ith coordinate, this is less or equal than e to the minus 2t times the semi-group of the derivative with respect to the ith coordinate squared. So let me interpret this. So what is PTF? This is the expectation of the function f of the random walk at time t, given that at time 0 I was in some fixed initial condition epsilon. Now, if I take di of that, that means that I am taking the derivative with respect to the ith bit in the initial condition, right? So I'm looking at what happens at time t, but now I wiggle the ith bit of the initial condition, and I see by how much what happened at time t changes, right? So if we believe that after a long time, this random walk goes to steady state, then after a longer and longer time, it should be less, and the distribution should be less and less dependent on the initial condition, right? So if I take the derivative with respect to the initial condition, this effect of changing the initial condition after a long time should get smaller and smaller and smaller. And that's exactly what this says, right? It says that if I change the initial condition, then this changes the outcome at time t by something like e to the minus 2t. Right? So this is just showing that I forget the initial condition at an exponential rate in some specific way. And again, this is going to be a computation. So let's take this for granted for now, and let's prove the Poincare inequality. So remember, what was the variance of f? It's minus the integral from 0 to infinity of d dt of the expectation of ptf squared. Now we can just use the chain rule, right? I could take d dt of ptf squared, that's 2 times ptf times d dt of ptf, right? So this is minus 2 times the integral from 0 to infinity of the expectation of ptf times d dt of ptf, which is just a Laplacian of ptf. So here we used 1. Here we used, in the first one was the first equality was the interpolation. In the second equality, we just used the chain rule and property 1. Right? Now we're going to use property 3. We're going to integrate by parts. Okay, so that's going to be 2 times the integral from 0 to infinity of the expectation sum I, the expectation di ptf squared. Right, so here I just integrated the Laplacian by parts, right? I get the sum of the derivative of ptf times the derivative of ptf, which is just a squared. And now, by the forgetting of the initial condition, this is bounded by what? Well, this is bounded by sum I of the expectation of dif squared times the integral from 0 to infinity of 2 e to the minus 2t dt. But that's just 1. And here we've proved the Poincare inequality. That's it. So this is the proof of the Poincare inequality by using this interpolation. And many of these things are just details, right? The intuition is very, very, very clear in some sense, right? I want to understand the difference between the expectation of f squared and the expectation of f squared. I interpolate between them by running a random walk, right? By running a random walk. And the key point here is that if I compute, to this part 1, if I compute the rate of change of the random walk as a function of time, that's related to the Laplacian, which is something like the derivative of the function that I'm looking at. And this is why you get the derivative on the right-hand side of the Poincare inequality. And the rest of this lemma, if you will, are just explicit computations. I guess, let's see now, I have 5 minutes, I can probably do most of that. So let me make some remarks. I think in some sense, this is the least intuitive part of the 4 lectures, okay? Because I have to introduce this laundry list of computations. And if you're used to such things, you know, like some things you get used to. If you're used to such computations, you see them everywhere. You know, these are standard computations. It turns out they hold in very, very general situations. This is so-called, for example, the 4th condition is called the Bakry-Emery condition, and it's something that you see in many different places. So if you're used to such computations, you start seeing them everywhere, and they're not funny anymore. But for now, I'm just going to compute them manually. But I want you to think of this lemma as a sort of calculus. This is a sort of payoff we need to do, right? We need to be able to do some computations, and at some point we will have to do it. But after this, we can just focus on the intuition. And every additional idea that I'm going to introduce is going to have a very clear intuition about how it works and how it relates to this proof over here. So that's a kind of apology. The other apology I should say is that, you know, anybody who has ever seen Boolean Fourier analysis will say that Van Handel, you know, I mean, in Boolean Fourier analysis, the Poincare inequality is a 0-line computation, okay? It really is absolute triviality. All you have to do is Fourier transform. What's the connection with Fourier transform? The Fourier transform, this is even true in Euclidean space. If I Fourier transform the Laplacian, it becomes diagonal. It becomes multiplication by x squared, right? And the same is true here. If I Fourier transform this equation, the Laplacian becomes diagonal, and then I can compute everything by hand. Right? And so everything becomes trivial if you do Fourier transform, which is, of course, one of the very basic reasons why Fourier transforms are so useful in this business. Right? Another way of saying that is that the characters of the group minus 1, 1 to the n are exactly the eigenfunctions of the Laplacian. Okay? Now, the problem with this is that even though this particular inequality becomes trivial if I Fourier transform, immediately in the next lecture, I'm going to show you an extension of this inequality to vector valued functions. And this was an open problem since 1960s, okay, to have such an inequality. And we have no idea how to prove such a thing using Fourier transforms. And what turns out to work is not Fourier transforms, but just these type of very basic probabilistic computations, right? So it will pay off to have done this very pedantic proof of a very simple inequality, because it's much easier to extend it to other situations.
Ramon, you have a couple of questions.
Yes.
So Galina asked, would 3 and 4 follow from 1 if you take 1 as the definition?
Well, I mean, depends on what you mean by follow, right? So 3 just follows from the definition of the Laplacian. 4, there is many different ways of proving it. I'm going to prove it probabilistically, but you can prove this by differentiating. But it would follow from 1, but not immediately. You'd have to differentiate and do some computations. Okay, so, but you could. But if I answer the question more generally, you never have to have a probabilistic representation. Okay, at least for this proof, you could use 1 as the definition of PTF. And that's a very natural way of thinking about it. You just think of the heat equation of the discrete cube. Who needs probability? Okay, this is just a differential equation, right? You know, it existed long before probability theory, right? I mean, Fourier had the heat equation, and this was before probability basically existed, right? Not on the discrete cube, but nonetheless. So in principle, you could just work with this. So this is called semi-group calculus, and it's a very useful thing to do. But the probabilistic perspective is going to be key for us, and you will only see that in the next lecture. Okay? But for this inequality, you could use 1 as a definition. What was the other question?
I think the other question was, does this work more generally for Efron-Stein, maybe in the non-Boolean case?
No. There is a very general theory of these things. I will give you a reference. There is a nice book by Bakri, Gentil, and Ledoux, which is called Analysis and Geometry of Markov diffusion semigroups, I think. And it develops these type of properties in obscene generality. Okay, these are very useful properties, but they do not follow from Efron-Stein. Okay, so Efron-Stein is much too simple. Efron-Stein only works when you have very special properties involved. But again, I'm immediately going to run outside of this theory in the next lecture. Okay, so that's the reason why I set it up probabilistically, even though for the purpose of this lecture, I'm only using these semi-group computations.
Ramon, I think the question was more naive. I think the question was, does it work for, if you take other product distribution, can you prove the Efron-Stein distribution?
Oh, yes, you can prove Efron-Stein this way very easily. Yes, absolutely. And then what you do, you can prove okay, if the question is, can you prove Efron-Stein this way, then the answer is absolutely yes. And here's what you do. You just run the same random walk as I did. Now, let's suppose you have independent coordinates, but with an arbitrary distribution, right? Then what you do in the random walk, you still attach a Poisson clock to every coordinate, and every time it clicks, you just sample from that distribution of that coordinate, and you replace the current value of the sample. That defines a new semigroup, right? Which is just like a random walk, but for more general distributions. And now you can repeat all of these things, and then you get Efron-Stein beautifully with the sharp constant and everything. So indeed, you can get Efron-Stein this way, though Efron-Stein has a very easy proof, which doesn't require this type of machine. But absolutely, Efron-Stein is a special case of this construction, right? But this construction is much more general. So I hope that answered the question. It is what, 2:31, so probably I'm out of time, right, at this point. You know what, I'll just, I'll resume next time. We'll take it from there. So in the beginning of the next lecture, I will prove this lemma for you, which is just a matter of computing some explicit formulas, and then we will move on and do something new. So thank you.
Okay, thank you very much, Ramon. I think we do have time for if anyone wants to ask a quick question. I guess the Q&A has been pretty active throughout your talk. So thank you very much. And we'll resume tomorrow at 9 a.m. California time.